be dealing with diffraction. Yeah, diffraction is something similar to light interference. As you remember, Friday, I've been doing a lot of analysis on light interference. So basically, the idea is you have multiple light rays that are interfering each other. So when you combine two or more waves together, then the amplitude will change. For example, you have your seawater, and then you have another wave from one side, and then you have the other wave from another side, and then when they meet each other, they will form. They will add up, meaning to say, if the maximum of the wave meets with the maximum of the other waves, then both of them combine together, and then the amplitude will be double. So when the minimum meets with the maximum, then they will cancel off. So for example, if I have my wave here. So I have my wave that looks like this, and then the thing is, I have another wave. When they coincide together, so I have my first wave, which is black in color, and then I have another wave which is maroon in color. So basically, this is wave number 2, and then I have wave number 1. This is my wave number 1. So when they meet each other, then the amplitude will be double. So the resultant amplitude, which will be drawn in blue color, will be this. Okay. So this will be like this. So meaning to say they will double. So this guy plus this guy, and then the result is here. And then this guy plus this guy, it will be even lower compared to the previous amplitude. And then another one, if I have my wave which are not in phase, for example, I have my wave here that looks like this, and then I have another wave which is inverted. Then the resultant, which is blue in color, will be this. The reason is because this guy is positive y, and then this guy, the other wave, is minus y. When we add both of them together, then the resultant wave is 0. It's a horizontal line. So meaning to say, if you translate, or if you shift the position of any of these waves, let's say if I have another wave which is green in color, maybe it begins over here like this, then the interference pattern will be different. Wait, I repeat again, yeah. So let's say if I have another wave which is in this position, then you have to add up everything together. Maybe this guy is 0 with the maximum, which is y. Then the resultant is over here. The resultant amplitude is over here. And then this guy meets with this guy, then the amplitude will be a bit, this guy plus this guy, it will be double over here. Not really double, maybe 1.7 something, the magnitude here. So it will look something like this. So you have to play around with the amplitudes lah. You have to maybe you can draw this using a graph plotter. So now my point is to allow you to remember how does light interference work. So as I mentioned before, you have for light interference, I have two slits over here, and then I have my principal axis, and then I have my screen over here. Okay. So let's say if you want to know the intensity at this particular position, and then you have to trace the light ray that is coming from here, to here, and then another light ray which comes from the second slit. So you have to do the vector addition of wave number 1 and then wave number 2. So meaning to say, if wave number 1 is equals to E naught sine omega t, then wave number 2 equals to E naught sine omega t plus the phase difference. So because the reason why is because you can see that there's a difference in path travel by both light rays. With reference to the light ray coming from S1, the source number 1, to the distance, I mean, for wave number 2, there will be an extra distance travel. Assuming that S1, the light ray number 1, is parallel to light ray number 2. So then here, this is our delta, which is the path difference. So in order to know this, you have to do the calculation. And then this is actually 2 pi over lambda times the path difference. So the thing is, you have to refer back to our previous lecture. So yeah. So moving on to light diffraction. So never mind, later I will repeat again for the interference of multiple waves. For the interference, for our previous lecture, we only discussed about the interference of two waves. Okay, a light ray coming from here, and then another light ray which is coming from here to here. Okay, so but today we are going to deal with more than two waves. So yeah, we'll do the calculus to find out the addition of the light waves. For example, I have my E1 plus E2 plus E3, and then plus as many as you can. So we will be evaluating this to find the intensity pattern. So you know that from our previous lecture, we have our intensity pattern, which can be written as E I naught cosine squared of theta. So theta is, let's say this is your principal axis. And then if you have another line, this is actually not a light ray. Yeah? This is just a reference line coming from here to here. And then the angle between the line here and the principal axis is the theta. So this theta is this guy. So hopefully you guys can remember this, yeah? And then moving on next, we have the diffraction. So of course, the diffraction involves allowing light rays to enter a small slit. For example, if I draw here, I have my single slit. We only have one slit, unlike the interference pattern, unlike the Young's double slit experiment or the interference slit. We have two slits for that particular case. Or again, I repeat, for Young's double slit, of course, you have two slits because the name of the experiment itself is Young double slit. Am I right? But now you have diffraction. you only need one slit. Okay, only one. So instead of drawing two slits, I have one slit. So the distance from here to here is the size of the slit, and then the size of the slit is denoted as A, or the width. The width, width, the width of the slit is A. Okay, and then this is your, this is the blocking material. Okay, this is the blocking material from here to here. The guy here and then the guy here will, they will block the light rays from traveling. They will block the light rays from traveling from here to here. So meaning to say, they will only allow the light rays to travel from here to the right hand side, from left to the right hand side, like this. Okay, but not this guy, yeah, but not this guy. This guy, this guy, and this guy will be blocked by the blocker here. I would say the blocker. And then the light ray from here will travel from here to here, and then it reaches the point here. As you know from Huygens principle, you can draw the wavefront, which looks like this, yeah. And then you have the wavefront, which is exactly on the slit window over here. And then on the wavefront itself, you can use Huygens principle to deduce that each point on the wavefront can be regarded as a wavelet. So at this particular point, you can draw the wavelets that looks like that. And then you can have as many points as you want. Maybe here, here, here. Okay? It's like that. And then you will discover that on the right hand side of the slit, you will see that the light ray is going like this. Okay. Yeah. So it is actually expanding. The light ray is expanding. The light rays, yeah, a collection of rays, they will expand. So assuming that your light source over here is coherent, meaning to say they are in phase. Meaning to say, whenever I say in phase, what it means is your wave should be like this. So the maximum here meets with the maximum here, the maximum here meets with the maximum here. This is the first light ray. This is the second light ray, and then you have your third light ray. You can as many rays as you wanted to, but the thing is they have to be coherent. So meaning to say their maximum must be at the same time. This is your time axis, yeah? This is your time axis. They must be the same at the same timing. The maximum will be, let's say this is 1 second. So the maximum will also be at 1 second. And then along the position axis, the maximum must be the same as well. So they are coherent. That's the meaning of coherent. The maximum must meet with the maximum. So in comparison with our daily life, for example, the white light that we are seeing every day in everyday life, the white light that we are seeing is a combination of rays with the different phase. So for example, the white light itself, let's say this is the white light beam. This is the beam, yeah? This is not the ray. So this guy, the light ray here, the white light ray here, the white light beam here consists of many wavelengths, consists of light rays with many wavelengths, wavelength 1, wavelength 2, because it is a mixture of colors, no? The rainbow colors, it's a mixture of them. And then as well as it is a combination of light rays with the different phase. So maybe wave number 1 is like this, and then you have a mixture of the other light ray, maybe like this. So the maximum does not meet with the maximums, not necessarily, okay? So it's a mixture of with many phases, many phases. So it's a combination of rays. But whenever I mention about coherent light, all light rays, so again I repeat, I repeat, let's say this is your coherent source. Okay, let's say this is your coherent light beam. Maybe this is coming from your laser pointer. So this is your laser window. This is your laser pointer, laser pointer. And then you can see the beam here. So normally the laser pointer will consist of a single wavelength. When you can have red laser, you can have green laser. So it consists of one wavelength. And then of course, the light rays in this particular beam will be in phase, in phase. So meaning to say, if I extract one light ray, then if I extract one light ray, then you will expect to see something like this. Sorry, not to see lah, to imagine. You can imagine that the wave are coherent. Maximum is in the same timing with the maximum. Maximum meets with the maximum. Okay. So that's it. Any questions so far? So that's the meaning of coherent light source. Yeah, that's the requirement for you to see light diffraction. And then when you want to light diffraction can be seen using our eyes. So basically, it looks like this. Yeah, if you look at my slide here, we have a coherent source, blue light source, and then it goes through a slit. So I have my slit over here. This is my slit. So there's a light source here, maybe a bulb. But the bulb here must be able to produce a coherent source. So when light enters the slit, so I'm sorry for this here. This is my slit. When it enters my slit, then it will expand like that. This particular phenomenon can be seen on sea waves, yeah? When you go near the beach, maybe at some point you came across two barriers. This is the first barrier, and then you have another barrier. So normally the light wave, not the light wave, yeah, the sea wave. For example, the sea waves are traveling from here to here, traveling downwards. And then once the wavefront passes through the slit here, you will discover that the wavefront will be expanding like this. So hopefully you guys are able to imagine this, yeah? Maybe you can search on YouTube, any YouTube videos maybe you can see this particular phenomenon on YouTube videos. Yeah. Okay. Next, let's dive into the technical part. Okay. So hopefully, at this particular point, you guys understood that whenever a coherent light source passes through a slit, then the light wave will expand at some point. It will expand over here, 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 like that. So meaning to say, if I redraw the wavefront, so the wavefront will look like this. Okay. So yeah. Okay. Mm, okay. So now I have my diffraction slit that looks like this, yeah. And then this is the width or the size of my slit, which is A. Not to be confused with your interference, where I denote the distance between the two slits as D, but now I'm using A to avoid confusion. So I have my screen over here. So of course, the light will travel from here to here, and then it will expand from this particular point, and then it will expand like that. Okay. So you'll be able to see the lighting on the screen. But the special thing is the intensity of the light will be like this. You are expecting to see the fringes. This is the dark region. This is the dark region. This is the dark region. So it is fascinating, yeah. When you look at the slide here, you can see there's a dark part here, and then the blue color, and dark, and the blue, and then here in the middle here will be the brightest, and then you have the dark position, and then you have the bright position, and then it goes on and on until it fades away. Okay, until the light fades away. As you go further away from the center line here, then it will fade. Okay, it will fade. Okay. The reason why you are seeing that kind of pattern is due to the interference of multiple light rays. So the thing is, we are using the same concept, which is interference. Basically, diffraction is a special phenomenon of light interference. So in general, it is actually light interference, but the diffraction itself is a special case of light interference. So meaning to say, if I trace my light ray, so let's say you know that there are many source over here. You can have as many source of wavelets over here, 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 here. And then if I draw the wavelet, it will simply look like this. So you have another one. So you have to go inside them, and then you will expect to see the resultant wavefront that looks like this. Okay. But now I will only explain to you, or I'll only deal with a small number of wavelets so that you can view this easily. Because in calculus, you try to approximate as many wavelets as you can so that you are able to approximate with the actual phenomena. But now we are looking at we are looking at the simple point of view. Okay. Okay. Let's say if I delete everything here. Okay. Okay. Just now I've shown you the diffraction pattern. Yeah. Let's say now I want to know the intensity of my light over here or over here. For example, yeah. Let's say if I want to know the intensity of light over here or over here or over here or here at the dark region. The thing is, you want to know the intensity of light. So in order to know the intensity of light, you need to deal with the calculus. So you have to imagine that the wavefront uh, consists of many sources of wavelets, just like the Huygens principle. And then you will have to consider the light ray coming from each of the wavelets. Sorry, from each of the light source. Okay. For example, so now I'm going back to my drawing. For example, let's assume that this is the light source. Okay, let's assume that this is the light source. And then I have another one over here. And then I have another one over here, over here, over here, and over here. But in reality, you have many points, okay? There will be many points. You have to include the contribution of those small points. But the thing is, for my explanation here, I will not include the entire points. I will just include some of them so that you can view the geometry, okay? So that you can view the geometry. Okay, now let's say if I want to study the intensity of light at this particular point, P. Okay, so now I extend my light, now I draw my principal axis as my reference point, which is at the center here. This is my principal axis. So obviously I define this as y equals to 0. And then I define another line extending from the reference point here, from here to here. So I need you to note that the black lines are not the light rays. The line here from here and the line here from here is just our reference, so that we can indicate the position of P using theta. So I have my theta here. So meaning to say, if I want to know the intensity of light here, over here, maybe this is P prime, then I have to draw another line from here to the point P here. And then I have another theta prime. So this particular theta characterizes the point P. Or maybe you can define P, you can characterize P in terms of Y as well. So maybe the point here, the elevation here is Y. Okay. Or maybe for this guy, the elevation here is Y prime. Just an example. So I'll delete this, yeah. Okay. Okay. Now, I need you to have a look at this properly, yeah. So now I'm drawing my light ray. Now I am drawing my light ray using my green color here. So let's say this is my source number 1. This is source number 1. This is source number 2. And then dot. You can have as many sources as you wanted to. You can include let's say 1,000 sources, or maybe you want to include an infinite number of sources. So you have to, if you include more and more, then your phenomenon will be accurate. Okay, so this is just for our imagination. Yeah. So the thing is, I only include some of them in my analysis here. So I'm not including many points on the wavefront. So let's say I am drawing the light ray that comes from source number 1. And then I have another light ray coming from source number 2. And then I have another ray coming from source number 3, directed towards point P. The reason why I'm doing this is because I want to study the intensity of light at this particular position. So I have to consider all light rays that are directed from each of the sources here towards the position P. So I have to include as many as I can. So now another light ray here to here, here to here, here to here. So each of the light rays here will be contributing to the intensity of light at this particular point. So maybe, maybe the light, we can write the light wave using this particular equation, delta E equals to delta E naught sine omega t plus pi 1. So this is the phase difference for my first light ray here. This is light ray number 1. And then I have my light ray number 2. So I can write this is for 1. And then I have another one, light ray number 2, which is equal to delta E naught sine omega t plus pi sub 2. And then I have light ray number 3, number 4, number 5, and so on. Meaning to say, the intensity at this particular point, I mean the resultant wave at this particular point is given by E at P is equals to delta E1 plus delta E2 plus delta E3, and you add more. So if you include as many points as you like, if you include as many points as you can, you include more, then your light ray will be, the contribution will be more, then the accuracy of your analysis will be better. So this is just like the calculus, yeah? Just like the calculus, when you try to compute the area of the area under the curve, you should discretize your x-axis, okay? And then you find the area of the box here. Then you have another box here. Find the area of the box here. And then find the area of the rectangle here. And then you find the area of the rectangle. I delete. And then you find the area of the rectangle over here. And then you have another one over here, and then this is area number 1, this is area number 2, this is area number 3, and so on. And then the total area under the curve is given by A1 plus A2 plus A3, and so on. So in order to have an accurate area under the curve, you have to reduce the size of the interval here. So you reduce the size of the interval here so that you are able to obtain an accurate solution. Okay. Okay. Now, it is basically the same idea. So the idea that you use in your calculus in order to calculate the area under the curve, you apply into this particular problem. So if you want to know the accurate light intensity over here, then you have to include as many light sources as you can. You include as many light sources as you can. So you have to draw another light ray coming from here, 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 here. Okay, and that's the idea. Okay. Now, I delete this. Okay. Now, any questions so far? Do you have any questions? Do I have any question in my chat box? Okay, no questions so far. I'm trying my best to explain this, yeah? So now, I need you to have a look at each of the light rays here. You need to look at each of the light rays over here, okay? So let's say if I zoom, this particular area, say if I zoom this, so this is my source number 1, this is my source number 2, then I draw my source number 1 here and source number 2 here. So meaning to say I'm zooming this, yeah? Let's say if I zoom this, again, I draw this again, yeah? I zoom this. And then my point P is somewhere here. And then I draw my light ray. Okay, I draw my light ray. Extending from here to here. So it will continue to P. So point P is somewhere farther away. It may extend beyond my screen here. And then I have another light ray coming from S2. So I'm doing the dotted line, meaning to say the light rays are extending beyond my screen. So my point P lies somewhere behind my screen here because this, I'm zooming this particular area. So as you can see here, my light ray number 1 and ray number 2, both of them are parallel to each other. In reality, they are not parallel. But the thing is, the screen is way farther than the slit here. Then we can assume that ray number 1 is approximately parallel to ray number 2. Plus, the size of the slit is small. Then we are allowed to use this particular approximation. So now I'm drawing another line. Here. So this is my delta A because it is from here to here. So it is delta A. Yeah? So from here to here is delta A. From here to here is delta A. So of course, from this particular point to this particular point, the size is delta A. So from here to here is delta A. Okay. Or maybe I can introduce you the differentials. It's easy for me to explain this. So instead of using delta, I'm using the differential of A. So this is dA. This is dA. So d is the differential. This is not any variable. This is a differential operator. So this is dA. a small portion of my slit width here. A small portion of my slit width. So this is DA. And then if I draw another line, so maybe I put my DA over here, DA. So this is my DA. Yeah. And then if I extend my drawing, if I draw a line here to here, and then you can see that the distance from here to here is my path difference between ray number 1 here and ray number 2 here. So both of them must be adjacent, or they must be next to each other. Yeah, they are not alternate, but they must be next to each other. So this is ray number 1, this is ray number 2. You can see that this is my path difference. So the path difference is given by, so you use, you know that this is your theta. The reason is because it is, you have to imagine this, yeah, because the distance of the screen is way farther than I mean the screen is farther away than the slit here. So the angle here from here to here, and then if I draw another line here, and then the angle from here to here, then if I draw another line over here, they are approximately the same. Let's say if I draw another one over here, and this is my light source, and then this is my principal axis. So the light ray is extending from here. The light ray is extending from here to here. So I'm zooming this, and then I put them over here. And then if I draw my horizontal axis here, so you can see the angle here, theoretically, they are not the same because they are pointed with the different elevation. Am I right? But since the screen is way farther, since the screen is far away from the slit here, then I would say the angle here is approximately the same with this. And then the angle here is approximately the same with this guy. This guy is also approximately the same with this. Because my distance from here to here is large. So I can assume this, yeah? So I have my theta here, meaning to say, this is my angle, this is my horizontal line. So my horizontal line here is parallel to my principal axis here. I have another angle here. So both of them here and here should be the same. So I repeat, yeah, my path difference will be sine of theta as O divided by A. So your O is, so my sine of theta, my sine of theta is equals to delta divided by dA. Okay, dA is the differential. Yeah, I repeat. Yeah, I need you guys to remember this. Yeah, dA is the differential. dA. So meaning to say, delta is equals to dA sine theta. So this is dA. I can write as delta A like this, or this is approximately the same as dA. I repeat, yeah. Hopefully you guys are able to accept this. Okay. This is my dA sine theta. Or you can write it as delta A sine theta. Okay. So you know that your delta is equals to 2 pi over lambda. Oh, sorry, your theta, your phase. So your, sorry, not theta, phi equals to 2 pi divided by lambda times the path difference. This is something that I taught you during my last lecture. I don't know, maybe if you cannot remember the equation here, then it's your problem. So meaning to say, if I try to help you to memorize this, then my lecture will take longer. So you need to accept this. Okay, you need to accept this. So this is your phase shift. This is your phase shift. Okay, the one that you put in your equation here. Okay, so you can write your phase shift as 2 pi over lambda times delta A sine theta. There are still students coming in, yeah? Your friends are still coming in. Oh no. Okay. So, okay. So now, hopefully you guys are able to understand how I derive my phase shift, my value of phi here, is equal to 2 pi over lambda times delta A, or I prefer to write it as dA sine theta. And then I repeat again, yeah. D is not a variable, yeah. I know you are the first year students. I'm willing to repeat this again and again. This is calculus. So this is not the distance or whatsoever. This D is the differential operator. And then I have 200 plus students here. I need you to, I clearly repeat that this is the differential operator. Yeah. And then A is the size of the width. And then dA is a small portion of this A, the length from here to here. Then if I take a small portion here, then this dA. It must be as small as possible. Okay. So you have this particular equation here. And then, okay, any questions so far? Maybe I can help you if you got problems in understanding this. I know it's quite hard for you to accept this, yeah. Maybe some of you are able to grab this. Maybe some of you are listening to me, but you are not able to understand this. And then maybe some of you are just entering my Webex room. I don't know. It's not my responsibility because you arrive here late. Then the thing, I'm not going to repeat it again. Yeah, an extra time. So it's not a particular equation. Yeah? And then next, what I'm going to discuss is I'm going to discuss about dark position. I mean, you see the interference. Sorry, you've seen the diffraction fringes. Yeah? So now our objective is to know where is the point on the screen such that the intensity is the minimum. So you know, if I draw my screen here, and then if I plot the intensity graph, it will look like this here. And then this is the dark position. This is the bright position. So of course, we have our equation just now, delta equals to dA sine theta. And then, you know, when you have interference, in order to have um, cancellation of the waves, the wave should be like this, yeah? The maximum must meet with the minimum. So in order to achieve the darkness, what you need to have is delta here must be equal to half of lambda. So it must be a multiple of half. Okay, so meaning to say I have my m plus half lambda equals to dA sine of theta. So meaning to say I have shifted. This is my lambda from here to here. This is my lambda. And then I shift another light ray here, another light waves or light ray. I shift half of lambda. So I bring this guy over here from here. At the point here should be the maximum. Am I right? So I push my wave here to the right hand side. And then the distance from here to here is half of lambda. Or maybe I can push to here. So it's about 3.3 over 2 lambda. Or maybe I push to the point where it is 5 over 2 lambda. So the thing is, it must be m plus 1 over 2. So m can be 0 or 1 or 2, 3, and so on. So yeah. So let's say if m is equal to 0, so my dark position will be half lambda. So 0 plus half is equal to half. Then equal to a sine theta dark. Okay. So this is actually a small portion of your interference, your slit width. This is A. Hopefully you guys are okay, yeah? Okay, next. Now I have covered until here. Sorry, until uh, should be somewhere around here lah. Okay. Okay. Next. So I have my slit over here. And then this is the slit, and then this is a blocker. It will block the light rays. And this is my. Now I need you to focus on the light ray, which is exactly traveling on our reference line here towards point P. Okay. And then there will be another light ray, which is over here. This is source 1, and then this is source number 2. Okay. Since this is our reference point, so it is located at half of A. This particular point is 1 over 2A. Sorry, the distance from here to here is actually 1 over 2A. So of course, the distance from here to here is 1 over 2A as well. It is 1 over 2A. Then if I draw another one, which is over here, and this is our path difference, which is equals to half of A sine of theta. Sine of theta. So it should be a multiple of half of lambda in order to achieve the dark position. Okay, let's say P is the dark position, meaning to say theta for the darks is equals to m plus half lambda. Okay, you can have this particular equation, or you can also have the one shown you previously. You can either use half of A, or you can also use dA. The thing is, the guy here will only be used in our light intensity. So yeah, it will be used in our next discussion, which is to know the light intensity over here. This is the differential form. And then the one that I've shown you previously is the general form. Okay, you can also use this particular equation. Meaning to say, in order to know the position of the dark points, so you have your interference slits, let's say, assuming that this is your dark position. So you want to know the value of theta here, but you know the value of A. You already know the value of A. And then you just substitute the value of A into here. And then you substitute whether you want to know the first order or the zeroth order. So meaning to say, if I go back to my slide here, this is the interference, this is the diffraction slit. So for this case, at the center here will be M equal to 0. Then I can see the first slit here. This will be M equals to 1, and then this will be M equals to 2, and so on. But the thing is, as you increase your value of M, then the intensity will become lower and lower. So here, if I draw this like this, it will looks like this, yeah. It will looks like this. Yeah, this is the intensity plot. Okay. Okay, now. So I have explained you for the content from here until here. You see, this is the general equation. For next one, and then next we will go through the single slit diffraction intensity. Before that, do you have any questions? You can ask any question. I'll rest for a while. Yeah, I'll take 5. But by the way, if you have any question, you can ask. Guys, I need you to bear in mind, okay? We have two different equations, yeah? Basically, they are equivalent. So we have this particular equation where we are using the half here. And then we also have another equation, which is this guy here. But instead of using my half of A, I'm using a small portion of my A here. So, okay, this particular equation will be used to derive our intensity for my next lecture. Okay, my next lecture for the next hour will be intensity of light. Okay, for the diffraction pattern, I'll be using this. Okay, and then you have another equation, which is this guy. This is just a simple equation using half of A here. So the purpose of the equation is to know the dark positions. The dark position can be here, 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 or here. So you can predict the angle. Sorry. So you can predict the angle from here to here. You can predict, yeah, using this equation. You can predict the angle here using this particular equation. In other words, you can use this equation to know the dark positions. Hopefully you guys are not confused with the two equations, yeah?